Omri Solan from Jerusalem speaks about Birkhoff's generic points on curves. Welcome, Omri.
Hello, everyone. I will speak on Birkhoff generic points on curves. If you don't know what any of these means, it's fine. I will explain everything. So I want to begin with a very simple question of maybe not very simple, but simple to define question of the Diophantine approximations. Say x is a real number. You can all see it. Okay. Say x is a real number and n is some big number, and we want to find rational approximations. Rational approximations. P over q to x, so that x minus p over q is smallest. And q is at most n. So we want to minimize this quantity. So how small can we make it? In general, for random x, for say not x in R, say x inside 0, 1. For x chosen in random in 0, 1, we can make this quantity wait, I write it. For random x in 0, 1, this minimum q less than n and p of x minus p over q, this is roughly 1 over n squared. So that's our beginning, and I want to state a few theorems, two quite old theorems on this minimum, and then we'll continue. So theorem A. No. Let x in 0, 1. No, not that order. No, I'm sorry. No, not what I want. Okay, let n be a big number. Be big. Then if we sample x we have uniform measure uniform measure on 0, 1, and evaluate the quantity 1.
So, Omri, I think your screen sharing disappeared. Somewhere.
Attempt to start a valid broadcast session. Go to application. I'm sorry. Okay. That's good. No. This. Okay. Now you can all see me. See again.
Yes, we're back.
Okay, so n is a big number, x is random in 0, 1, and evaluate this minimum of x minus p over q for q less than n and p, the absolute value. Okay, and then multiply by n squared. And I want to show, and okay, the theorem claims then this quantity converges in distribution. It's the distribution of this number. It's a random number. Converges in distribution to, as n tends to infinity, to some fixed measure mu. Some to mu, where mu on probably zero infinity measure. Okay, so that's the first theorem, which states that for very big random, therefore, if we look on this error of the best approximation of the best approximation with denominator up to q, we get then the error up to is 1 over n squared, and is something times 1 over n squared, and the something distributes in a way that is known. There are it's known. Is there a question? Okay, and mu can be computed, but I don't want to write any formulas here, so I will not do that. Okay, that's the first theorem on the Diophantine approximations that I want to introduce, and the second is theorem B. Okay, before I say what is theorem B, I want to encapsulate what is theorem A. I have the same scale of approximation. I want to approximate with denominator up to the same n, and x is random. Theorem B is going to be the opposite. I'm going to sample one x on random, and then try to approximate it on many scales. Okay, so let x inside 0, 1 be a random number. Okay. Okay, I have a new page. So x is a random number, and now we'll try to approximate it for many different n's. Consider for every n, this 1 over n, no, not 1 over, this n squared minimum of q less than n and p of x minus p over q. And now I want to take this quantity for many different n's. I want to choose n by random. So now I think of x as random and fixed. Random number, fixed. It's not going to enter into the probability that I'm saying now. I consider this number for random n, for random n equals e to the power of t. And okay, for n equals e to the power of t, and t, x is big random, x is random, t is big. So we choose for every no, not what am I doing? So this is too big, and we want to consider okay, that's not relevant. Okay, we want to consider this quantity n squared x minus of this minimum we have. So we choose n equals e to the power of t, and t is inside 0 capital T uniform. And now this is a random variable which depends on t. For every t, we can compute this quantity. And what I claim is that this quantity converges to the same mu in distribution. T tends to infinity. So I did a weird thing. I chose one x, and then I wanted to approximate it in many scales and see what is the random, for a random scale, how good can I approximate my number x. And then I did another thing which is weird. I chose my n with this weird distribution of exponent of some uniform number. Why did I do that? So if I choose just n to be a random uniform between 0 and t, then there would be no real difference. There will be a small difference between if we had n uniform n uniform 0 t, then if q turned out to be half n, then the best approximation would be very correlated for a lot of values of n. And so this random variable must be dependent on x, because it's very correlated. So I cannot expect some convergence in distribution. And so I would not have any. Does that make sense? If someone lost me and I'm just speaking nonsense, stop me, please.
Can I ask you a clarifying question?
A bit louder, yes.
So you said you choose x at random. Can I take any x, or it only works for some x?
It works for most of the numbers x, but I will talk about it. In fact, I don't know any natural x that we know that this theorem works. We can prove it. I mean, no, I very much believe it works on pi, but it's the very next thing I'm going to say. Okay.
So just to clarify, you have two mu's, and this is the same measure in both theorems.
Yeah, here and above and below this mu equals this mu. It's the same measure.
Okay. Interesting.
Great, thank you. Okay. And so now we can try to. This is an excellent question because it was my very next bullet. We want to try to somehow extend these two theorems, theorem A and theorem B. One we sample. We want to somehow extend those. And the most natural question is, do we have a specific x we know theorem B works for? Not a random one. And I do not have any. Is there a question?
Yes, Irene.
Is there a question? Okay, no, I guess not. Okay. I don't have any specific x that I know. I don't think we have a good example for x, for a natural x that it works, but I think that for every specific x that you give me, either I have a good reason to believe that this theorem works, that it works, or very easily I would be able to prove you that this theorem fails, and yet I have no good example. Okay, so extension 1, find specific x for theorem B. Okay, so the second natural thing, the second way to extend theorem B and actually theorem A as well, is by changing this random randomness, this uniform way we sample x. So extension not below.
Omri, so sorry, before you talk about extensions, can you clarify? So these are these two are your theorems.
No. These are not
these
very
come
old
from
theorems which I know, and they were probably known for many years, many years, but I don't know I don't know the references.
Okay.
If you know, I'll be happy. But
yeah, if anybody knows the references, I'll be interested.
okay. So extension 2. So for both theorem, we can try to sample x via different measures. That is another extension. I believe there are results in theorem A and perhaps theorem B, but I don't know. But we'll get to that. Sample x via different measures for theorems A and B. Okay, and that's another possible extension. And the last extension I want to somehow discuss, and it's more vague than the previous two, is extension 3. So we can try to approximate different objects by different things. Different objects by different approximately different objects. We can try not to approximate numbers, but instead approximate vectors. We can actually even we can try to approximate numbers by different things, not only rationals but algebraic. And that's somehow the motivation I picked for this talk. So what I want to discuss now is algebraic approximations.
Sorry, can I ask a question?
Yeah.
I don't know if it makes sense, but what about changing the way you randomize T to randomize the N? Sorry, it make sense?
It makes sense. It makes sense. I believe it will be similar, that unless you do something bad, like that if you take not the measure of n but the measure of log n and it's too concentrated, then I believe it will be wrong. Otherwise, I believe it will be true, but I don't have an idea how to. I don't know currently how to do that. It makes sense, and well, the fundamental approximations is a much larger area than what I told. There are many ways to extend it, other than these possible extensions. I tell only these because that's what leads me to in my talk.
Sure. Thanks.
Does anyone know what will happen if we try different measures for n? Okay. I don't know. Okay, so let's d be an integer, and x be a real number, n big, and now we can consider algebraic numbers. Alpha inside R is k d. I want d. Is d algebraic if exists p. No. If there is a polynomial of degree in integer coefficients of degree deg p less or equal than d, and p of alpha is 0. Okay. So okay, and then we define the height of alpha is the maximal coefficient in absolute value, maximal coef in absolute value of p. Okay, probably without 0. That's a fine
You
enough
mean any polynomial that alpha vanishes on it, right?
I can define it with minimal.
No, the height, like you need to choose a polynomial. So
okay, for the minimal polynomial. So minimal poly. Okay, we choose minimal poly. The collection of polynomials vanishing when alpha has some minimal one, and we choose the minimal maximal. We choose the minimal degree and the minimal degree. There is exactly 1 after multiplication. We can define a height. It really doesn't matter what exactly the height is, but there is one natural p, and we choose that one. Does that make sense? Okay. And so now, okay, yeah. And so now we can ask what is the minimum over alpha d algebraic with height of alpha less than n of x minus alpha. That's a question. We can ask it. And now let's go over theorem A and theorem B, and I'll say what is known for this question. So by Shah, I don't remember the year, proved an analogous of theorem B, of theorem A. He proved an analogous of theorem A. It's slightly more complicated than what I stated. There is not there is no one fixed measure, but it's somehow varying on X. And so I don't want to state the exact formulation of what he said, of what Shah said in this language. I will state it in homogeneous dynamics in a few seconds, but minutes. I'll state it in next in the talk, but now I'll say Shah proved an analogous theorem A, and together with Andreas, we proved an analogous for theorem B. Okay. So now, okay. So that's actually not the way I like to think on the problem. I don't think of it as algebraic approximation, but I think of it as something in homogeneous dynamics. So now I want to tell you.
Excuse me, Omar, just 1 second. But to have a result of this type, you multiply this minimum by n to power d plus 1. Is that what happens?
Yeah, thank you very much.
Okay. Just checking.
This is approximately 1 over d plus 1. And
n over d.
N over d plus 1, and it makes sense because how many numbers alpha we possibly have that may approximate our x. So we need to choose some polynomial with coefficients bounded by n. And so we have this many polynomials. And so we expect these numbers to distribute somehow evenly in the interval. And so we expect that the best approximation with algebraic numbers to be of this order of magnitude. Okay. Well, let's start a new page. Okay, so now I want to transform all of these problems to homogeneous dynamics because that's what I do. So okay. So now any correspondence will take standard approximation Diophantine approximation problem and transform it into a question in lattices, which I like better. Okay. So say we have x and n. X and n, we want x minus p over q small and q less than n. Okay, so this is not very different than asking for, it's different, but it's not very different than asking for wait, I had okay, it's not very different than asking for qx minus p to be as small as possible. It is different. I multiply by q, which may change, and so it's not exactly the same minimization problem, but it's sufficiently similar for this discussion. Okay, now if we look for the collection of no, I want black. If you look for the collection of p over q inside z squared with qx minus p. Okay, so less than cn and q c1 over n, cn inverse, and q less than n. Then we can see that we have a lattice and some convex condition on our vectors. Okay, so why I wrote qx minus p less than cn inverse? So it makes sense if I want to ask is there an approximation such that qx minus p is less than c, which is an equivalent question to trying to minimize this quantity. Okay. So now we want I want to make this condition somewhat more pleasant. But I will more simple, but I then will make this z squared more complicated. So let us multiply, instead of q, let's consider this n inverse, n inverse, 1 minus x p over q, and that is exactly what we that is equal to n x minus qx. No, it's p minus qx and n inverse q. Okay, and now we want this to be inside minus c times minus 1, 1. Okay, and so if I want to measure for how many x's there is such a vector p over q, pq, such that if I multiply my vector pq by these two matrices and it's then inside this set, then I will just I'll ask if can I copy? Can I copy? I don't know. Okay, n inverse 1 minus x 1 z squared intersect with minus c times minus 1, 1. Okay, so now we have a very simple set that we want to intersect with some more complicated lattice than before, and we transform our question of understanding this minimum, is equivalent to understanding the distribution of this. Okay. So what now? So in what space does that live? That lives inside the space of lattices. This wait, not here. This is two-dimensional of covolume 1. And we want to ask, how does this lattice distributes? How does this lattice sits inside the space of lattices? And so theorem A wait, before I say what's theorem A, the reason, let's call slower. A two-dim lattice denoted by x2 the space of such denote X2 is the space of such lattices of dimension 2 of covolume 1 lattices, and it has a measure, has a Haar measure. Measure. Okay. So theorem A corresponds to if we take the lattice 1 minus x 1 z squared and multiply it by some n inverse for random x inside 0, 1. So this converges in distribution as n tends to infinity to the Haar measure. Okay. Okay, so I want to draw a picture because that's because I like pictures and it helps me see things. So this lattice denoted by lambda x. And so we have the curve, this small curve of lambda x's. Lambda x for x inside 0, 1. And then we apply to this not big for this moderate curve of length 1, we apply to it the matrix n inverse this matrix. And now these curves become larger and larger. We can see that this curve become larger and larger. Somehow I don't know, it stays in the space. It become larger and larger and larger. I can't draw it, but it becomes larger and larger. And the claim is that, and now theorem A corresponds to the equidistribution of this curve inside the space of lattices. Okay. And now theorem B. Theorem B, we had some random point x inside 0, 1 random. And now we took lambda x. Lambda x was this lattice. So we have lambda x inside our lambda x. It's a point, just a point in the space of lattices. And we apply to it e to the t, e to the minus t, for t in 0, t. So now we have a big curve. We have, I'll draw another picture. We have a curve of lambda x's. We choose a point, and when we flow, we flow in the e to the t to the minus t direction a lot of time. I again cannot write, but the claim is that these partial orbits, which are these partial orbits, equidistributes. And now this follows from Birkhoff ergodicity theorem. That these are just pieces of orbits are what Birkhoff ergodicity theorem deals with, and by Birkhoff ergodicity, these curves okay, in this t to infinity to how. Okay. So now, okay, any questions? Okay, no questions.
So again, the equidistribute for typical X, right? For generic
typical X and larger T's.
Yes.
Okay.
Okay.
So now I want to.
So it's different from theorem A, because theorem A really all large N.
Yeah, this is it's different from theorem. Yeah.
Okay.
Okay. So now, before I continue to our polynomials, to algebraic approximations, I want to discuss another approximation problem. Let x1 xd inside R the d and n greater than 0, big, find, minimize x1, okay, x1 p1 plus x2 p2 plus xd pt for p in z to the d with norm less than n. Okay, this is another approximation problem. We have some plane in the space. We have some plane in this plane, and we want to find an integer point, a bounded integer point, which is as close as possible to this plane. Okay, and so it doesn't really matter if we multiply our vector x1 to xd by a scalar. So we'll assume x1 equals 1. It will be convenient to me. And now we can apply the Dani correspondence for this problem as well. It goes via very similar lines, and we get that we want to understand the lattice Dani correspondence, and we want to get and we get it. We need to understand the lattice z to the d 1 1 1 x2 xd, and now we have the matrix. Okay, so this will be of order of magnitude n to the d minus 1, and it's d minus 1 because although we have n to the power of d possible p1 to pd, this value ranges from some order in this value has order of magnitude n for random n to the minus. This value has order of magnitude n for random p1 to pd, and so if we have n to the d values between n to the d values in range of size n, we expect the minimal to be of size n to the 1, n to the minus d plus d minus 1. Okay, and so now we have n to the d plus d minus 1. N to the d minus 1 and inverse and inverse. Okay. So the Knee correspondence tells us that to understand how this quantity distributed after multiplied by the correct normalization factor, we need to understand the distribution of this lattice. Okay, and now why I introduced this particular Diophantine problem. Okay, so back to algebraic approximations. Back to algebraic. If we have x minus alpha small and x minus alpha is small and p of alpha equals 0, then we would expect that p of x is small. And we need to understand some orders of magnitude, but it follows. And so instead of trying to minimize x minus alpha, we'll try to minimize. So this is equivalent to trying to minimize p of x for p inside z. Oh no, my variable is x. It cannot be. Alpha. No. Y is fine. For p inside zy with deg p less than d, less or equal than d, and max coef of p less than n. Okay, and now this is just the previous problem. This turns out to be trying to approximate this problem. We try to minimize this kind of expression. Minimize. Okay, so if p equals, that's not a sum I equals 0 to d yi pi, we try to minimize some pi x to the power of I, and so we get to the same approximation problem we had for functionals, for planes. And so we're interested in, so apply Dani correspondence to it. Dani is a person. Dani correspondence. We want to understand the lattice n to the, well, it was positive, n to the d, and inverse 1x squared x to the d, 1 z to the power of d plus 1. So in order to understand algebraic approximations, we need to understand this kind of lattices. Okay. So now I'll just call this vector gamma of x. And this I'll call u of gamma of x. I mean, maybe u of x1 to xd equals 1, 1, x1 to xd. Let's denote gt equals e to the dt, td, e to the minus t, e to the minus t. Okay, and now I get to the actual theorem sharp proved. For every gamma from 0, 1 to r to the d, analytic image of gamma not contained in some hyperplane, then if we consider gt u of gamma of s z to the d plus 1, I wrote here z to the d plus 1, should be d plus 1, yeah, I wrote it. This for s uniform on 0, 1. So this converges as in distribution as t goes to infinity to Haar measure. Okay, and okay, and okay, and the theorem of okay, before that, this theorem was okay. This theorem is nice, but it's not as generic as possible. In particular, this condition of analyticity and not contained in some hyperplane can be relaxed in many ways. The analyticity shined Peng-Yu Yang relaxes to only 2D times the differentiable, and this not contained in some hyperplanes, it can be relaxed. There are conditions that in which it can be relaxed, and I don't remember who did it, but Dimitri was one of them. For small d, I think. It can be relaxed. Okay. So
well,
this is
it's also Nimish and Peng-Yu for arbitrary d. They wrote in another paper.
Okay. Okay. And now the theorem that and now for theorem B, theorem together with Andreas Wieser. For almost all x inside S inside 0, 1, GT U of under the same conditions. Under the same conditions, GT U of gamma of S Z to the D for T inside the uniform in 0T for T uniform in 0D in 0T. So this converges again to Haar measure. Yeah, almost surely. Okay. So now I have about 15 minutes, right? I would like to explain some of the ideas behind this proof. Behind this proof, and actually most of what I'll talk will be, many of what I'll talk, okay. There is some big strategy that all of the results I've read in the topic actually follow. So, okay. So suppose, so the general strategy goes as follows. Suppose let's note this measure by mu t. So suppose mu ti tends to some mu has some. Suppose there is some partial limit mu ti which tends to mu partial limit. Okay, so suppose mu ti tends to mu in some partial limits, then the proof is composed of three steps. The first step, in the first step, we prove some unipotent invariance for mu. Okay, now we may use Ratner theorem. And deduce that mu is composed of some algebraic measures. Mu is combination of alg measures. And now we have two. We want to prove that there is no escape of mass. It could be that somehow some mass escapes to infinity. And so the second thing we need to prove is that there is no escape of mass. And the third thing, which in our proof was very similar, so I call it 2' because I want to advertise that these are very similar problems. We want to show that any algebraic orbit that mu of certain sets, certain orbits, is 0. Okay. So now you have a choice. I can talk about one and I can talk about two. I won't have time for both of these. And so you have a choice. I need someone to choose.
I
two
don't
is
know if I choose. So maybe can you choose the one which is newest compared to what
Okay.
is
Yeah, that's
the
one
most
is
original contribution.
yeah. Okay.
compared to the-
So let's talk about two. Two is more. One is not standard, but it is by now standard, more standard, and two is more original, I think. So how can we? So let me draw a picture. This is the S direction, goes from 0 to 1. This is the T direction, goes to infinity. How can there be any escape of mass? So escape of mass by Mahler compactness criterion says that there is some V. And in this, we think on each point is GT U of gamma of S Z to the D plus 1, I think. Okay. So what do you want to say? Okay. So if there is V inside Z to the D plus 1 with if there are many with GT U of gamma of S V small, then for okay, so we have sorry. We have a orbit which goes like this, and each vector v covers some shape. I don't know, some sort of shape, for which t and s it is small. And so we want to rule out the fact that there are somehow, and so okay, in order to have escape of mass, we need to have some sort of conspiracy that there are a lot of vectors that for most s's, in some scale, there are a lot of vectors that want to conspire against this very specific s, and somehow a lot of vectors would cover our same vector s. Okay, so now I'm going to do something which is not entirely trivial, which is counterintuitive at first. I'm going to go back to fixing t and vary s for every v and t, v in z d plus 1, t in 0 infinity, denote I v t equals s in 0, 1 such that gt u of gamma of s v is less than 1. So the first thing is the first problem that I want to address is there might be lattices which escapes because there are two small vectors. Somehow this vector v which makes a lattice high in the cusp is not unique, and so I will make a completely false but will help me to make the idea assumption assumption for every lattice lambda, there exists at most one short vector. I don't want to deal with the case that there are somehow two vectors shorter than one. At most one v in lambda with without 0 with norm of v less than 1. It's completely false, but it will help me make my point. Okay, so we get that these intervals I vt in which a vector v is smaller than 1, they are disjoint. So this assumption is completely false, but using ideas from Klein-Coullis no divergence theorem, it is sufficiently close to the truth for this purpose. Okay, so now we have our many intervals, and let's define also I vt epsilon, where we have the same thing less than epsilon. Okay, another assumption which is not that far from being true. I vt and epsilon are intervals. Okay, so now we have our so it's also not true, but there'll be a union of not too many intervals. Okay, so now we have we can see that the rate gt expands u, gt expands expands u of x rate e to the d plus 1 t. Okay, and so if I change s by less than e to the minus d plus 1, if change s by e to the minus d plus 1 t, this matrix will not change by a lot, and so this vector will not change by a lot, and so roughly it's also not exactly true. The length of I vt is larger than e to the minus d plus 1 t. So now I will separate these intervals to two different cases. I vt big if if I vt is larger than e to the minus d plus 1 t plus square root of t, and is small otherwise. Okay.
Okay, I mean, maybe we can wrap it up somehow within a minute
Yeah.
or two. Because we
I'll
still
say
have some time for questions. Just
I'll say, let me say one sentence. The big intervals will be very rare. We can bound the total length of them, and it's finite, and so Borel can tell us that there are no big intervals. That okay, the for random S, any random S will be contained in finitely many in big intervals, and the small intervals shrinks in a very fixed rate, and so they're mostly independent, and so they cannot conspire against against any S. Okay, that's it.
Okay, so maybe we'll use this break to thank Omri and have a round of applause, either virtual or just like this. This very interesting work and very interesting talk. I encourage all of you to look at the paper, which is posted. Any questions to the speaker? So maybe I have two questions. One, I think both are natural. Maybe we can answer fast. One, if you put weights, will the same work? Because you mentioned that the rate of expansion is the same for this curve. Is it crucial?
Yeah. So these arguments work, I believe. I think 2 and 1 and 2. Okay, unipotent invariance you'll have anyway. It's a very simple argument. No escape of mass. I think you'll have as well. But the linearization we do in 2' slightly fails. So we cannot. So I believe it should be something very similar should work, but I don't. We haven't worked out the details. But
okay. Interesting. Okay, and another question is maybe naive, but you have theorem 1 or theorem A, which gives you convergence once with respect to one parameter, and then theorem B convergence with respect to another parameter.
Mm-hmm.
So maybe there is theorem C, which implies both theorems, which kind of double convergence, something like this. Have you thought about it, or I mean, does it make any sense?
We mentioned it, but we haven't really put any real thought about it.
Okay, these are all my questions. Anybody else wants to?
Then I thought that if T goes up much faster than S changes, then something may work, but I don't know.
Mm-hmm. Okay, thank you.
I have a question.
Yes, please.
So you're using polynomials, right? I mean, you're trying to, you have this family of polynomials, and you want to minimize values of this function on these polynomials, of this number on these polynomials, right?
Yeah.
So what about maybe different families of functions? So like this is like the question may be, so maybe there cannot even be a dynamical interpretation, like something really special happened here, right? When you had this 1x, x squared, so on in the matrix. So maybe for different families of functions, it cannot work, but...
No, you can have any analytic functions instead of 1x, x squared. This gamma from 0, 1 to RD had to be, but it doesn't have to be a polynomial or anything.
No, I'm not talking about gamma. I'm talking about the way, like in the previous, like one of your questions. I think this is the one you're in right now. So you want to minimize, you want to minimize alpha evaluations in polynomials up to a certain height, right?
Yeah.
So you basically have a growing family of functions, which is the polynomial, like this is the polynomial. So maybe, I don't know, like I don't have a concrete example in mind, but maybe like a different family of functions that increases, that you have more and more. And
if your family of functions is additive, then the same will work. It's just the same. If it's not a lattice, you need to tell me what it is.
Like, can you say that again? If what?
If your family of functions is additive, Here we had polynomials of certain degree,
Right.
and the crucial
Right.
fact for me was that it's additive, so we can put some lattice structure on it.
Yeah. Yeah.
If
Yeah.
it's
Yeah, I
not
think-
that, I don't know what to say.
So these tools cannot work, basically.
I'm not saying that. You need to tell me what it is, and then I'll.
Yeah, if the function, if the family is not specified, then these tools cannot work. But yeah.
Well, you need to take, if you take linear combinations of coordinates of these non-degenerate, non-planar curves, then it will work. That's what Omri was saying.
Yeah. So it doesn't have to be like the coordinate functions themselves. It can be
Not,
other-
any components of this analytic function, as long as you don't have linear dependence between them.
Right. Mhm.
Okay, well, maybe I think we are out of time. We can still continue, but let me thank Omri again and push the recording of